Okay guys, let's talk about uncountable numbers and why they're useful, okay? First I'm going to talk about an example from probability to nail this down, and then we'll get into the real meat here. Okay? Alright, so, let's say I'm flipping a coin, alright? Head, with head and tails, okay? And let's say that I'm just going to call these instead by numbers, okay? Like head is 1, tails is 0, okay? So, I can represent it here as like, okay, half the time with this coin, I will get heads. Okay, half the time I will get 1, and half the time I'll get 0, right? And I'm using this x1 here to represent basically that, okay, 50% of the time from 0 to 0.5 here, excluding the endpoint, it will be 1, and the rest of the time it will be 0. Second flip, same deal, right? 0 to 0.25, 0.5 to 0.75, that will be 1, that will be heads, and here we have tails. Same thing with the third flip, okay? And one thing I've also done here is I've made it so that all of these guys are clearly independent of each other, right? Because your first flip doesn't bias your later flips, okay? As in, if I get heads, then I'll be sort of in this space right here of probabilities. I'll get heads on the first one, and I'll be, okay, 50% here, 50% here. Same thing if I got tails, 50% heads, 50% tails for the next guy. So on and so forth. Okay? Okay, so that we set that up, alright? Now, one important question to ask is, well, what should be the average number of heads that I will get? The way I can figure that out is I can figure out, okay, I'll define this thing yn, okay? And yn is the sum of all of the heads and tails that I've gotten from the first n trials here, the first n times I flip the coin, divided by the number of trials, n. And this will give me my average, okay? Alright, and one thing about this is we already know what this should look like ultimately, right? As in, what should this tend towards as n gets larger and larger? We have a very clear sense that as n gets larger and larger here, this should tend towards 1/2, right? As in, if here's 1, 0 down here, then this should be like 1/2. As in the future, as I take very, very large samples, this should look just like 1/2. For the number of heads I get. Half the time I get heads, half the time tails. Okay. Now, the thing is, that's what our intuition says. That's our gut feeling here. And that's what experience tells us, right? You know, the more times you do it, the more times, the closer you are to 1/2 with the average number of flips. But let's actually look at the way I've set things up. Let's actually look at what happens concretely for particular points of yn here. If I do, let's say, yn at 0. Okay? What does that look like? Well, let's see here. That's going to be, x1, x2, so on, xn divided by n. What are these values at 0? What is this when I evaluate at 0? Well, for the first guy here, at 0, yeah, that's going to be 1. And for the next guy, yes, at 0, I'm again 1. And for the third guy, 1, 0 again. 1 again. And so on. I have n ones here, and it equals 1. That's weird. Like, this should go to 1/2, right? Definitely. Yes, definitely should go to 1/2. But, no, it doesn't. It actually goes to 1 of them. But yeah, that's the point. This is a point, This is a screwy endpoint there. Like, well, let's do another one. Let's do yn at 1/2. That should work. That should work. Okay, let's see here. What is x1 at 1/2? 1/2. Not 0, 1/2. This is going to be, let's see, oh, I'm excluding the endpoint here, so that's going to be 0. Alright. Then for the next one, it's including the endpoint, 0.5, so yes, it's 1. And then down here, it's including the beginning endpoint, so yes, 1. And it's actually going to keep being 1s, given the way I've set this up, okay, if I keep splitting it with these half intervals like that. And what happens here, like, oh, I've got, how many 1s do I have? Well, I have 1, 0, and the rest are 1, so this is n minus 1 over n. Which, as n gets very large, that's going to approximate 1 again. What about some other just number, like, excuse me, some other number that's like a decimal, like yn, decimal, like p over 2q, okay? Where this is just some number. It could be something like 125,000 over, that's 2 to the 80th. Could be something like that, okay? What happens there? Well, let's see, I'm going to change this just a little bit. I don't know. Alright, so what happens there? What does this look like? Well, what this guy will look like is he's going to first have a whole bunch of zeros, maybe an occasional 1 in there because he might have been like in the middle of some guy like this. So maybe a couple 1s in there, but let's just say it's all zeros at first. But then at a certain point, we're going to get 1s, and then we're going to keep getting 1s, okay? And what this will look like is something like n minus 80, right? Because to the 80th, we know that at least after the 80th coin flip, we are going to get 1s all the way. This will be n minus 80 over n, and as we see clearly, oh yeah, this right here converges to 1 as n gets larger and larger. So everything like that. Or, I guess what I should have written here is not just as 80 in the example, it's n minus q, where it's that guy right there. So, what does this say? Anything of this form will be 1. So if I try to draw that up there, it's like, okay, that's going to include 1/2, and it's going to include 1/4, and 3/4, and an infinite number of things, actually. Okay? The hell. I thought yn was going to 1/2. That's what I get in experience. Why am I getting all of this noise here? Why is it shooting up to 1 all of the time? What it seems like all of the time. What the hell's going on here? Now, this seems like a really serious problem. How can this converge to 1/2? Well, that doesn't. It doesn't, it seems like. Well, let me also mention another fact here. We have a problem with this stuff right here. This is p over 2q. And guys, believe me, I could have made this a ton worse for us. I could have made it so that these guys are so organized that it could have been on every rational number, okay? That is, every rational number, it will equal 1, all right? And it's still, in a sense, all these independent coin flips here. That's a good exercise for you to do. How do you arrange these guys so that all the rational numbers will equal 1? And don't think there's any like screwy business here with the endpoints here about the fact that this is 0 and this is, and I excluded these guys or something. If let's say I excluded all of them on both sides, or this is like, you know, excluding 0, excluding 0.5, excluding 2/8, then when you add up all these guys, it would have given you 0. So instead of having a bunch of sort of hairs shooting up here, you would have had a bunch of like little valleys shooting down to 0 here, okay? So there's nothing about this that's special. There's nothing about like these these p over 2 to the q form numbers that's special here. It's something just inherent in probabilities that we're going to get like a mess like that. Okay. Is there anywhere this is not a mess? Is there anywhere where this actually makes sense in a consistent way? Give us the answer we hoped? Well, yeah, the irrational numbers actually. That's for sure. The irrational numbers will actually, I'm not going to prove this here, but they will actually at least most of them, the vast majority, will half the time be, get heads, and then the other half will get tails, okay? If you do something like 1 over pi, I don't know where to write it, but 1 over pi or 1 over e, something like, here's like 1 over pi, and here's like 1 over e. It's like, okay, half the time this will be in there, half the time it won't. Half the time this will be getting heads, half the time it'll be tails. So, actually, we do get a ton of points where it's 1/2, but we also get a whole ton of points where it isn't. So, what's going on? What is going on? Help! Help! Well, why is it that yn on these special numbers, actually what you want to say is yn, I'm going to rewrite this a bit. Yn on p over 2 to the q, any number like that, this converges to 1. But any number yn irrational, it goes to what we want it to. And guys, I could have made this again worse, where this could have been rational. Let's figure out why this is. So let's talk about cardinality, guys, and how it would solve this problem. One thing is, we want to sort of get an idea of, is there some way of talking about size when you're dealing with infinite sets? Okay? Like, in some sense, I really feel like, the even numbers are smaller than the number of natural numbers. Natural numbers are smaller than the number of rational numbers. Rational smaller than reals. The x-axis is smaller than all of the numbers in the 2D plane. Like that. There's some sense they feel that way. I don't know if that actually makes sense. I don't know if that's just illogical. But it feels reasonable to say something like that. But maybe some of these things are not reasonable. Let's investigate this idea, okay? Can we generalize the idea of smallness, of size, to infinite sets? Well, what do we do when we compare one size to another? Well, one thing we do is we count, right? I'll say like, okay, I've got like 4 books up here. How do I count those off? It's like 1, 2, 3, 4, right? I sort of pair my fingers together with the number of books here. Okay? And we would say that there are fewer books than I have fingers in my right hand, because there's no way for me to pair all of these books to my fingers, okay? So it's sort of like I have a set of a white book, a blue book, a brown book, and a black book. Okay? There's no way I can take these guys and go to all my fingers, right? Which I'll just give numbers. Right? There's no way to pair off all of these guys with all of these. I can do something like this, but then I'm missing 5. I can do something like this, where it's like white, and then maybe go back to 1, and I'll do blue there, and then brown, and then I'm missing 4. There's no way to do it, okay? There's no way to basically pair every one of these guys with one of those. In a sense, there's no way of making a function that takes in my books here, and goes onto everything here. Okay? There's no way, I'm always going to miss something. You know? I'm always going to miss something. I guess in this case it's actually 5. Okay, that seems kind of important, this idea of like pairing. And, you know, we're used to this idea, right? You know, like you have a dinner table and you want to know how many spoons there are, but you don't know how many forks. Well, if the spoons are always next to a fork, well, congratulations, now you know. So this is a really important idea, this idea of pairing things off. And again, that's what we do when we just count. You know, you pair off your fingers with whatever happens to be out there in the world. Okay, so the idea that we're coming to is maybe we'll define things as having the same cardinality if basically, I guess what I'll say is if there exists a function from x to y, that, let's see, completely covers? I guess I'll use that term. I'm going to try to keep this not too technical. It covers y, then x has a greater than or equal to cardinality than y. Okay? That's a lot to take in there. That's a lot to take in. But the idea basically is, let's say I have some function that goes from x to y. Let's say it's all my fingers. Okay. I'll leave that as is. From x to y. And I can cover all of y with x. As in, I can cover all of these books here with my fingers. I can perfectly pair them off in that way. Then I see, oh, the cardinality of my fingers is bigger than the cardinality of the books. Okay? But on the other side, though, because I can't do that the other way around, I cannot pair off all of the books to my fingers, then this has a smaller one. Okay? Okay. So I hope that's at least semi-clear. I'm going to now move on. I'm going to try to actually apply it to some of these guys here. Alright, let's talk about the evens and the natural numbers, okay? And by the way, guys, it's not clear so far that this is even quite going to give us anything here, alright? What are the evens to the naturals? Well, I can actually pair off, obviously, I can pair off all the natural numbers to the even numbers. That's really easy. All I have to do is just, whenever I have an x, which is a natural number, I suppose I should do this n, just send it to 2n, right? So 1, 2, 3, 4, 5, and I have 2, 4, 6, 8, 16, really easy. 1 goes to 2, 2 goes to 4, 3 goes to 6. I see every natural number is paired up with an even number. What about the other way around? Can I do the other way? Yes, yes. That's actually pretty straightforward. All I have to do, well, basically, if I have a function that goes from the evens to the naturals, it actually just works the same way. I could just do 2, 4, 6, 8, 16. Excuse me, that's not how these numbers work. 10. And I can just divide everything by 1/2, right? 2, 3, 4, 5. Okay? So the evens and the natural numbers have the same cardinality right here. Okay? So that doesn't feel like we're getting very far, right? That doesn't seem very useful in any way because, again, this feels like it's larger, right? What about the natural numbers and the rationals, okay? That's a much larger set, the rationals, it seems like. You know, that's basically everything of the form PQ where P and Q are part of the natural numbers, right? Any fraction of that form. Can I pair off all the natural... It's obvious that, you know, Q pairs off to the natural numbers, right? That's really easy. I can completely cover that because this guy actually contains that, so I'm not even going to bother making a representation here. But what about the other way around? Is there any way I can set all the natural numbers, make some kind of mapping that's all the natural numbers onto the rational numbers? Pretty straightforward, actually. Pretty straightforward. What's a good way of organizing the rational numbers? Well, we have a numerator and a denominator. So up here I'm going to put numerator, over here I'm going to put denominator, and I'm at 1, 2, 3, 4. 1, 2, 3, 4. And I'll just make numbers. 1, 2 over 1, 3 over 1, 4 over 1, 2, 1/2, 1/3, 1/4, so on and so forth, guys. You guys seeing this? It's repetitive in a lot of places, clearly. But I will cover every single number here, right? This 2x2 diagram here will contain everything. Let's see, I feel like finishing it up. And it's 3/4? Yes, 3/4. Okay. How do I cover this? With all the natural numbers. Pretty straightforward. All I do is I'll take 1 and I'll put it right here. Pair it up with this guy. Then I'm going to start over here and I'll go like this to that guy. So 2 goes to 1/2, 3 goes to 2 over 1, 4 goes to down here at 1/3, and then it goes diagonal like that, and we keep going like this. You can see that eventually this list will cover any particular rational number you want to talk about here. All of them, without exception. Alright, so, alright, now it seems like, okay, like the even numbers, 2 n, that's a good way of calling the even numbers, is, you know, same cardinality, same size as the natural numbers, and natural numbers are the same size as the rational numbers. Okay, that doesn't really seem very useful. Like, yeah, okay, we've got these things, but whatever. What about the reals? What about the reals? We'll find the reals are a bit different here. First off, just a reminder, what are the reals? The reals are all the rational numbers, so everything like 4 and 3/7, but also irrational numbers like pi, square root of 2, etc. Tons of stuff. Alright, now next argument is going to be a little bit complicated, so I'm going to simplify things a bit. So just a little reminder here, guys. These are the real numbers right here. All that stuff. Okay, so one thing I'm going to do to simplify this situation, guys, I'm just going to deal with the interval 0 to 1. Okay, why am I allowed to do that? Well, we can very easily pair off these numbers with all of the real line. So let's say here's the interval 0 to 1 just turned. Here's like the positive real axis right there. Here is a point right here, just some point just hanging out there in space, but it's, you know, level with 1. And basically I can just take, alright, I'm going to pair off every point on the real numbers with some point on this interval here, okay? On the positive real numbers to this interval. So like this one gets paired off to that one, this one gets paired off to that one, this one gets paired off to someone very, very far away. And you can see that, okay, well, 0 to 1 is obviously paired off with the real numbers. These guys are of the same cardinality because this guy contains that guy as a set, and this guy can be stretched onto all of that, okay? And if you want the negative 1 numbers, that's again really easy. All you do is you make this 0, this 1/2, and then you can just pair off the stuff from 1/2 to 1 that way. Okay? So, okay. Again, missing a point here, but it's really just 1 point, okay? Like, you can fit that in if you slightly change the construction appropriately. Okay, so I'm just going to deal with this because I see that I have the situation here where the real numbers are some way equivalent to 0, 1. In this, they have the same cardinality. And over here I have, here's the rationals. I'm going to look at the natural numbers specifically. And by the way, that's sort of connected to the rational numbers. So, are these two guys the same cardinality? Are they? Let's take a look. So, let's say we did have a map, okay? Obviously, this guy is at least as big cardinality as these guys, right? Because the real numbers contain the rationals and the naturals, so obviously this is at least as large cardinality. But is it bigger? Is it bigger? Well, suppose it wasn't. Suppose this was the case, okay? And there was a way of mapping all the stuff, let's say, all the stuff from the natural numbers onto 0, 1, like this, okay? There's some way of pairing off all the natural numbers onto every single number from 0 to 1. So that includes like 1/4 and 1 over pi, and 4 over e squared, etc. All sorts of stuff. So I can make this list, okay? I'll make this list, this enumeration, where these guys are paired off. So again, 1 goes to 1/4, 2 goes to 2 over pi, 3 goes to 4 over e squared, 4 goes to 1/2, so on. Okay? We have this way of mapping everything inside of there onto there. Okay, that's all very well and good. You know what I like to do? You know, it'd be fun. I'm going to rewrite this, except in decimal places. But let's not use decimal because those are a little complicated. Let's use binary. Okay? So I'm going to rewrite these guys in various binary representations of B0, 1, 0, 1, 1, so on. This one's going to be B1, 1, 0, 0, 1. This one's going to be 0. This is, by the way, these are wrong. These are wrong. Just in case you were wondering. You know, but I have some list that goes on and on like that. Okay? And I decide, alright, so this is my list. It sends 1 onto there, 2 onto there, 3 onto there. Well, you know, I'm curious about something here. Can I make an element from these guys that might not be in there? Let me see. Let's see, 1. What if this first interval here, this first guy, I make a new number, and the first place I'm going to put in a 1. And the second place I put in a 0. And the third place I can flip this number right here and I get 1. And the fourth place I flip that 0 and I get 1. And I keep doing this, okay? As in, the way this number is defined here is I take the nth position, so the first position of the first guy, the second position of the second guy, third position of the third guy, so on. And I flip the value, okay? Now I want to know, because supposedly this mapping right here covers all of the numbers from 0 to 1, is this one included? Is it? Well, no, it isn't. No, it isn't. Because where will you fit it in? You can't fit it into the first guy. Because this is 0 and that's 1. You can't fit it into the second guy. You can't fit it into the third guy. You can't fit it into the fourth place, so on and so forth. This guy, this number, this element from in 0 to 1 is not listed. There is no natural number which includes this in its list. So, therefore, the assumption that I could make this sort of function, this sort of enumeration of the real numbers, is false. It can't be done. Because if I were to assume it were true, I could find this, this example which proves that it would be false. Okay? We have a contradiction, and therefore this and that have different cardinalities. Okay. Okay. So that's an impressive and bizarre thing. You might want to spend a lot of time on your own thinking about that. Now, you might be wondering, like, well, okay, right, like, these numbers are different. How does this relate to the problem? Well, I'm getting there, okay? One thing you should notice, though, is the real numbers and the rational numbers are a different cardinality. And one thing you can also show is the real numbers without the rational numbers, the irrational numbers, as in the rational numbers deleted from there, this will actually have a different cardinality. This is a larger cardinality than the rationals, okay? That's important. And the fact that this guy can be listed with the natural numbers, that is also important. So, okay, let's move on. Let's talk about some very basic measure theory in a very simplified fashion. Okay? Now, alright, I want to find out the size of various sets, right? Like in 2 dimensions. How big is a circle? How do I find that out? Well, one way of at least estimating it is to say, alright, I'm going to cover this with a box. And that will give me an estimate for how big this is. And I say, okay, well that was fine, but I want to do a better estimate. You know, I want to make a very much tighter tiling of this guy. And I'm only going to include blocks that contain some part of this. So, like, I'm going to include only these boxes that I am outlining now. Okay? So I'm going to exclude all the ones outside that slightly darker outline, which I really hope gets caught up in the video. And you guys can imagine I keep doing this, right? I keep splitting this stuff up and I keep refining it. Okay? What am I doing here? What am I doing? The idea is, okay, the measure of this circle, of this, I'll call it the disk. The measure of this disk will be less than or equal to the sum of all of the area. I'll call those, let's call that, yeah, I'm going to do I'll do measure. The measure of all of those rectangles. Alright? Clearly. As long as this completely covers it, those little rectangles, little mosaic pieces I'm covering it with, then I know, okay, because those pieces contain it, I know that the measure of the disk will be less than or equal to it, okay? One thing I would like to find out, though, is what is the size of the disk? What is the exact area? Well, one way I could do that is I could take better and better, more and more precise pieces, smaller and smaller ones, right? Like we do in calculus. And I'd like to know, like, okay, what is like the smallest possible one? So one thing we do here is we say, okay, the measure of the disk, that will actually equal the, I'll call it the lower bound on all of these sums of rectangles that contain D, okay, that contain the disk. Okay, that makes sense in its way. Like, okay, this is going towards some smaller and smaller quantity right here as I make these more and more refined, these different little pieces here. And it feels like, okay, whatever the lower bound is on this sum of rectangles, the sum of the measure of those rectangles that get better and better approximations, that will be the measure of the disk. Alright, that sounds fine. That sounds really useful. Let's make this a little more simple, okay? Let's go to one-dimensional case, okay? Where instead of rectangles, I'm just going to be using intervals. Alright, and you can imagine, like, oh, what's the length of, like, this set of intervals here? Well, like that, you could just cover that with various intervals and find out that. One question I have is, how big is a point? How large is a point? Well, that's not too hard to figure out, okay? The measure of this point. I can cover that with an interval from like -1/2 to 1/2. And I get 1 there, right? And it's going to be less than or equal to 1, obviously, then. I can also do it with an even smaller one, if this was like -0.1 to 0.1. 0.2. And I could do it, smaller and smaller, so on and so forth. I can make this interval indefinitely small. And I find it, oh, okay, yeah. The measure of a point, because it is smaller than every positive number out there, less than or equal to all positive numbers, that implies that it is equal to 0. Smaller than anything with a positive value, you are 0, therefore. And negative values are excluded here. There's no such thing as negative measure. Okay. So that's nice. Alright, well, what about the natural numbers? Like, how big would be, all of these guys from like 0, 1, 2, 3, so on. How big is that? Turns out not much larger. Not any larger. One way I can figure that out is I'm going to cover all of these guys with a set of intervals that get smaller and smaller. Okay? So around 0, I'm going to put an interval of size 1/2. Around 1, I'll put an interval of size 1/4, 1/8, 1/16, so on. I then find out, okay, measure of the natural numbers. What is that? That's less than or equal to all of these intervals here, which equal 1/2 to the n, n is equal to 1, to infinity. Which, if you remember what geometric series are like, guys, it's like, here's a rectangle that is a square, that's 1 by 1. This is 1/2. This is 1/4, 1/8, 1/16, 1/32, so on. It's going to equal 1, guys. It's going to equal 1. So, okay, that's great. Now, one thing I could have done here, guys, is I've also could have made these even smaller, right? Instead of starting at 1/2, I could have started at 1/256. And then I could have done 1/512, so on, okay? These are powers of 2. And I could have found, oh yeah, the measure of the natural numbers is less than or equal to the same sum, except starting at Oh, I forget what that is. I think that's like 8 to the power of 8. Maybe 7, who knows? That guy in the comment knows. Alright, so this right here will turn into what? This will turn into 1 over 120. Gotta look too caught up in numbers here. 256. That is equal to 1 over 24. Yes, 1 over 28 actually. Excuse me. Alright, smaller number. And you guys can see that I can just make this smaller and smaller, right? So again, the measure of the natural numbers is smaller than any positive number. So it's 0. It's 0. This whole set of points just equals 0. It's a big nothing. Okay. That's a little weirder, but again, not that strange, because again, it's like, well, yeah, right, obviously. It's just a bunch of ones, you know, it's nothing. It's just a bunch of zeros. Well, here's where things turn. Here's where things turn. Here's where things go a little berserk. Let's talk about the rational numbers. Okay? So again, here's all the rational numbers. I just drew them all. So, you know, 0 and 1/2 and negative 1/4 and negative 32 over 57, whatever. All over. All over. Okay, they're everywhere. How big are those guys? What is the measure of the rational numbers? Should be 1, right? Right? That's everything? Not quite. Not quite. Because we also have the real numbers in there, right? Let's also, actually, let me restrict this a bit. Let me restrict this. Let's just do 0 to 1 right here. Let's just talk about the rational numbers inside of there, just to make life a little more straightforward. So all of these guys, all over everywhere. Okay? Well, that can't be 1, right? Because, you know, this isn't everything. There's also the real numbers, or the irrational numbers. So, excuse me, 1, 0 to 1, remove Q. This is all the irrational numbers inside of there. So, we know that the measure of 0 to 1 is 1. Like, that's just the length, clearly. But what about these guys here? What about just the rational numbers in 0 to 1 and just the irrational numbers? That's complement, so that means everything besides that. What are these guys? Because they can't both be 1. They can't both be 1 here, okay? They have to be one or the other. You know, it's either 1/2 for both of these guys, or it's 0, 1, or it's 1, 0. What is it? What is it? Well, let's observe a fact. How can I cover up all of the rational numbers? Any way to do it? Well, obviously I can just take, you know, 0 to 1. I can just do 0 to 1. And that would cover up everything. And I said, okay, yeah, so the measure of Q01, all the rational numbers inside it, that'll be less than or equal to the measure of 0, 1. Clearly, okay, less than or equal to 1. Anything better I can do? Any ideas that maybe this gives me here? Any ideas that gives me? Well, why was it I was able to do this with the natural numbers, because I could sort of like match them all up with 0 goes to 1 as 1/4, this goes 1/2, and then 1/4 with 1, 2 goes to 1/8, 3 to 1/16, so on. Do something similar here? Yes, because it's countable. I can do the exact same thing I did there to the rationals. I can make a nice little list of all the rational numbers because they're countable. Because I can put them in a one-to-one correspondence with that. So this goes to like, 1 goes to like 0.5, and 2 goes to 3 over 18, and 3 goes to 4 over 7, and so on and so on. Great. And what that happens then is I can cover up 0.5 with 1/2. I can cover up 3/18 with 1/4. Cover up 4/7 with 1/16. And I can keep doing this with indefinitely smaller intervals. Like that. And I find out that, oh, I've actually covered up everything here. I've covered up every one of these guys. I'll say I at 16 here. Cover this guy up with 16, and this guy up with 132, and this guy with 164, so on. And I find, oh, the measure of the rational numbers, since I was 16, this is less than or equal to 1/8. And that's not all. I could make this indefinitely small. So I find out the rational numbers from 0 to 1 are less than every positive number. Less than every positive number, so that means they're 0. They're 0. This guy is 0. And if that guy is 0, and if this is 1, and this is everything else, this guy is 1. So, almost every goddamn one of the numbers from 0 to 1 is irrational. At least if we do it by measure, by this particular standard. And again, okay, like, that's fine, that's weird, but whatever, Ray. How does that get us anywhere? Where did our probability function screw up earlier? Where did it go wrong? Right? The idea was, I had basically, this is the average number of times I get heads, alright? And I thought this is going to 1/2, right? It's going to something nice and straightforward, 1/2, right? Like that. Where every single value here goes to 1/2. But then I found out that it screws up. It screws up at a very definite set of points. It screws up at all of the points yn at p over 2q, that this right here always converges to 1. So what this converges to as n approaches infinity, this converges to a function where it's like it's 1 all of the goddamn time. For every one of these sorts of numbers, because they're everywhere. They're everywhere. And even I could have made it worse, right? I could have made this even worse. I could have made it like the rational numbers. And like everywhere it converges on 1. Like I didn't show you that construction, but it is possible just by moving things around a little bit. And I thought, okay, I feel like it should be like 1/2. That's what it is from experience. But I don't get that. I get all this stuff here. But one thing I also found is that, but on the irrational numbers, 0, 1, remove q, on all of those ones, this equals 1/2. It does exactly what I wanted it to. On all of this stuff, it's good. It's good. And now I know that, this thing right here, this average, yes, it goes to 1 on the rational numbers. It goes to what I want it to, what I expect it to go to on the irrational numbers, and that's all that matters. This stuff's garbage. This stuff's nothing. This stuff is measure 0. Measure 0. This stuff is measure 1. It's everything. It's all of the probabilities. So when I do this convergence, okay, it's not converging everywhere. It's doing what we in mathematics call it converges almost everywhere. Almost everywhere. It excludes a certain set of measure 0, in this case, either rational numbers of this form, or we just flat out the rational numbers, and but it converges everywhere else. It converges almost everywhere. And that's why we care about this stuff. Because when we deal with a very straightforward probability problem, what is the average number of times when I flip a coin, I get it to land on heads? I run into major difficulties. Incredibly large difficulties, it seems. And then, but using this tool of almost everywhere, which we got from measure theory. When the measure theory used is distinction of countable and uncountable to distinguish the irrational numbers from the rational ones, we found out, oh, congratulations. This stuff is garbage. This stuff is nothing. This is dust. I can throw it away, and I only care about this. That's the only kind of convergence that matters. The convergence almost everywhere.